The rate of heat transfer depends on what mechanism of heat transfer you're talking about. In the last example, we talked about conduction, which happens when you have solids in contact with each other. And then the textbook qualitatively discussed convection, because convection is based on fluids where the thermal energy is transported from one part of a fluid to another by the actual fluid molecule moving from one part to another. So you have to learn a little bit about fluid dynamics in order to discuss it more properly. And then the third type is this thing called radiation. It turns out that all bodies, whatever phase it's in, emit some amount of electromagnetic radiation. And there are deeper descriptions as to what frequency or what wavelength of EM wave is emitted based on the temperature of the body, etc., etc. But we're going to focus again mostly on the rates of heat transfer, which is sort of the radiative power, so to speak. It's the amount of heat or energy that you're emitting over a certain amount of time. And it turns out the rates of heat transfer is described by this formula here. A couple things to point out. This first thing is called the Stefan-Boltzmann constant. It's a universal constant for all material. Depends on your area that you're radiating from. There's this thing called emissivity, which depends on the surface you're emitting from, and also therefore the material. Some surfaces are able to both emit and absorb more easily than others, and so we capture that in this term that again we measure and you look it up on the lookup table. And finally, you got this temperature, but unlike the conduction formula, this isn't T1 minus T2. It's not the temperature difference we're talking about. It's just an object and it just radiates. So this is actually related to the absolute temperature, which is measured in Kelvin. So make sure you convert everything from degrees Celsius into Kelvin. I've added in a couple bonus because it is the last of the chapter, I suppose, just to tie things in together through this whole thermal unit. But let's do the actual question first. The actual question is quite simple. We're just trying to apply this formula for radiation. So in this case, we have a heater that heats up and glows red and therefore emits a certain amount of energy. So we're given the surface area, we're given the emissivity, we know the required power, we need to know its temperature. Rearranging that formula, we need the fourth root, or might be easier to type in your calculator as raised to the 1/4 power. Emissivity has no units. Watts is 1 joule per second. And as you expect, you would get the final temperature in Kelvin. So if you want to convert that to Celsius, it'll be about 350 degrees Celsius. Not something you want to touch. Fairly straightforward. It's got that funky power. Gotta remember to use Kelvin, but that's radiation. But then they did say neglect the temperature of the environment. Why does that matter? Well, let's look at extension 1. So now, beside this heater, which radiates out to everywhere, we place a piece of ice next to it with a certain amount of area facing the heater. And the question is, how much net heat transfer? The key point here is net, because while the heater is putting heat into the ice because it's so hot, the ice is not at absolute zero. It's at 0 degrees Celsius, but it's also at 273 Kelvin. So it's going to have a little bit of radiation that comes out of the ice, some of which the heater will absorb. So while the heater is giving the ice a whole bunch of heat, the ice gives the heater back a little bit of heat. So then the net heat transfer is going to be the difference between these two. You have to consider both things are interacting. Moreover, all this power that is emitted by the heater, only a certain area of which is exposed to the ice. So for both of these, we're going to use the surface area of the ice that's exposed to the heater. So the radiation coming out of the heater is not the full 360 watts because only part of that area is exposed to the ice. So we have to calculate again, but we do know the temperature of the heater. But also, the ice only picks up a certain percentage of that, which is captured by the emissivity of the ice, minus the area of the ice facing the heater, the emissivity of the ice, multiply the temperature of the ice. And so that's how much the ice emits, but only part of that gets absorbed by the heater because the heater doesn't have 100% emissivity. Seems like a little bit more going on, but the main point is when you have things transferring heat via radiation, it's very likely that both of these objects are going to be emitting heat at each other, and you have to account for both of those before you can tell how much heat is actually transferred on the net. Again, using temperature in Kelvin. So you can see that, yes, while the ice does put some heat transfer back to the heater does a lot more because you got the temperature to the fourth power. So the net rate of heat transfer is 70 watts. Depending on how different these two temperatures are, it would be a significant error in neglecting the radiation of the ice. And so given this rate of heat transfer, how does that affect the ice? So in order to melt the entire block of ice, we need to supply a certain amount of heat, which is given by the latent heat, as we talked about. And assuming that the area stays the same as it melts, maybe it's in a big long tube or something like that, we can use the same power, which I should also point out that as the ice melts, you're still at 0 degrees, so the temperature of the ice remains valid. So really just a way to tie the whole chapter together. Watts being joules per second, we end up getting quite a long time, which is more than an hour. Of course, this is only dealing with the heat transfer through radiation. The other mechanisms, such as conduction and convection, is happening at the same time. So in actuality, to get this lengthy melting time, you really do need to remove the effects of these other heat transfer methods. So maybe the result isn't as surprising as you might think. And also, you can hopefully appreciate how if the temperature change as we go, that will change the power, and then it'll feed back on itself and change time, and so you will need to use differential equations to treat that properly. But we won't get into this in this course. A little bit lengthy, but hopefully that does tie the whole unit together, and we're almost done.